All right, so for this video lesson, we're going to be doing quantization of charge. All right. So we already talked about Millikan's oil drop experiment back in Unit B. And is what he did, he put a oil drop, or he sprayed oil droplets into essential oil canister, and he applied an electric field in there as well. And based on the strength of the electric field, he could control the rate at which the oil drop would fall up until the point in which the oil drop was not accelerating. And this is when he was able to, at this point when it was not falling, he knew that the electric force was equal to the force of gravity, right? That's recall from Unit B. But yeah, so just to talk about the oil drop in a little bit of detail here, and just a refresher there, recall that Millikan used X-rays and radium to ionize the oil droplets in the chamber. Once they were ionized, he measured the single droplets, which he knew the mass of, and by measuring the single droplets, he was able to detect individual electrons. So again, he applied an electric field and analyzed how the electrons would fall in response to a varied electric field, okay? The presence of the electric field would slow the falling of electrons or the oil drops until it was at a constant speed. So that's where we have the force required to move a charge through an electric field. Fe is equal to E times Q. And the force of gravity from physics 20 is mass times gravity, right? In this case, this is the mass of the oil drop, which he knew the mass of. And from that, he was able to calculate the charge of the electron, right? That was a pretty big discovery. And that was in 1913. All right. So you guys need to watch the mechanical universe of Millikan's oil drop experiment, just to give you a little bit of a refresher of this experiment. It's about 30 minutes, so please take the time to watch that. All right, so moving on to topic 15.3, the discovery of the nucleus. So this is the famous experiment associated with discovery of the nucleus is Rutherford and his scattering experiment. Okay, this was in 1909. Yeah, so from the results of this experiment, he concluded that the atom is composed of a positively charged core, which is termed the nucleus. And this is where the majority of the mass is located, as well as the protons and neutrons, right? The nucleons. And then we have electrons, which will orbit that positively charged nucleus. Okay, so we're going to talk about the gold foil experiment a little bit. You guys should have watched the development of the atomic model video from last lesson. So hopefully you have a little bit of a background on that. Yeah, so as what we see in this experiment, so Rutherford used radioactive elements, which would emit alpha particles. So an alpha particle is essentially, well, it is a helium nucleus. which has 2 protons, 2 neutrons, so it gives a mass number of 4. Okay, we will talk about that a little bit more in nuclear physics. Okay, so anyways, an alpha particle is a helium nucleus. So he used radioactive materials that would emit alpha particles. And these alpha particles were emitted onto a gold foil. And he would measure the angle at which those particles were scattered. Okay. Now, because the alpha particles are much more massive than the electrons, he did not expect there to be a large angle of scattering as he was shining the alpha particles onto the metal foil, right? Much more massive than the electrons. So it should just kind of, if we consider the momentum from unit A, it shouldn't have much of an effect on the alpha particles, right? It shouldn't cause it to bounce right back at him, which is what he noticed. Prior to the gold foil experiment, a lot of the information was based on Thomson's model of the atom. Remember, Thomson's model was the plum pudding, where he had electrons kind of embedded throughout. And the rest was positively charged space, right? So even in this positively charged space, he did not expect it to be so dense, again, to cause such a large angle of scattering, right? If it was distributed evenly throughout the electron, the positive charge, then he would expect a little bit of the alpha particles to return towards him, but not to the extent that which he saw. And after the results of this experiment, he mentioned this in his lesson when he was teaching at a university. And he said that the results of this experiment were as incredible as if you fired a 15-inch shell, a gun, at tissue paper, and it came back and hit you. So he was just as surprised from the results of this experiment as anybody, right? So that's pretty fun. Okay, so this is, again, just another image of the gold foil experiment. So we have alpha particles being emitted on this side, traveling left to right. So the majority of the alpha particles were able to pass through. However, when the alpha particle were to strike the actual nucleus of the atom, it would bounce back at a larger angle of scattering, okay? So after observing these patterns, including the particles bouncing back, this indicated that the mass of the positively charged area must be concentrated in a very small area of the atom, which is positively charged. So this is called the nucleus. Okay, so that was a pretty big discovery for the time. And again, that was in 1909. So Rutherford was actually able to calculate the size of the nucleus and the distance between the charges using the conservation of energy and also Coulomb's law. So remember, if we have a change in energy, this means there's work being done in the system. So work is equal to force times distance, right? Change in energy is equal to work, and work is equal to force times distance. Therefore, change in energy is equal to force times distance. He also used Coulomb's law. So we know that the electrostatic force between two charged objects is inversely proportional to the distance between those charges. F is equal to K Q1 Q2 over R squared. And instead of it being a radius, it's just going to be the orbital distance, right? So we can substitute in D for R there. Okay, so our formula, force is equal to K Q1 Q2 over D squared. And let's manipulate delta E is equal to force times distance. So it's written in terms of force. So divide both sides by D. And we get force is equal to change in energy divided by distance. So we will substitute that into this formula here. So delta E divided by D is equal to K Q1 Q2 divided by D squared. You can solve for change in energy. We'll just multiply both sides by D. That will cancel. And we are left with change in energy is equal to K Q1 Q2 over the distance, okay? So just a couple notes here. So change in energy, this can either be potential or kinetic, right? So E is going to be energy at the orbital distance. And D here is going to be the distance between charges. Okay, and again, this formula is not on your formula sheet. So I would write this down on your personal formula sheet and also be able to derive that formula if needed on a unit test or the final, okay? Okay, so let's get into some practice problems here. So in a Rutherford scattering experiment, some alpha particles, so alpha particles have a charge of 2e, right? So Q of alpha is equal to 2 electrons, or 2 times the elementary charge, which is equal to 3.2 times 10 to the negative 19 coulombs. Okay, these alpha particles are scattered almost straight back from gold foil. So we know, so gold is Au, has 79 electrons. And if we multiply 79 times 1.6 times 10 to the negative 19, we will get a value of 1.264 times 10 to the negative 17 coulombs. Okay, estimate the maximum possible size of the gold nucleus. So we are looking for the distance here. If the initial energy of the alpha particles was 1.6 times 10 to the negative 12 joules, okay, and again, we are asked for the distance here. Okay, so using the formula that we derived on the last slide, we know that EP, or energy, is equal to K Q1 Q2 divided by D. We need to write this equation in terms of D. So we will multiply both sides by D. And divide by E. Okay, now we have it written in terms of D. So we have the distance is equal to Coulomb's constant times Q1, Q2 over EP. I'll just substitute in our values. So Coulomb's constant, 8, not a very good one, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared, multiplied by Q1, which would be our alpha particle, so 3.2 times 10 to the negative 19 coulombs, multiplied by the charge of the gold nucleus, 1.264 times 10 to the negative 17 coulombs, divided by the energy, which is 1.6 times 10 to the negative 12 joules. Okay, punch this into your calculator and you should get a distance rounded to 2 sig digs of 2.3 times 10 to the negative 14 meters. All right, couple more to go. So the charge on a tin nucleus is 50 electrons. So Q tin is equal to 50 electrons. So if we multiply that by the elementary charge, we get a value of 8 times 10 to the negative 18 coulombs. It is an alpha particle. So Q of an alpha is 3.2 times 10 to the negative 19 coulombs. We know the initial energy is 1.6 times 10 to the negative 12 joules. And we're asked, how close can that alpha particle get to the nucleus of the tin atom if it has this particular amount of energy, right? Anytime that you have two positively charged objects coming towards one another, they naturally want to repel. But if we have energy, it can get pretty close, right? Before it does repel, kind of like what we've seen in Rutherford's experiments. Okay, so we will use the same formula here, and I'm going to write it in terms of D. So D is equal to Coulomb's constant times the charge of tin multiplied by the charge of the alpha particle divided by the energy. So we'll substitute in those values. D, I'm just going to leave K for Coulomb's constant. Charge of tin, 8 times 10 to the negative 18 coulombs. Charge of the alpha particle, 3.2 times 10 to the negative 19 coulombs. And the initial energy is 1.6 times 10 to the negative 12 joules. Okay, we'll punch those into our calculator and hopefully you get a distance of 1.4 times 10 to the negative 14 meters. Okay, so not overly hard, but as long as we have that formula, it's nice and easy, right? So again, make sure you're able to derive that if needed to on a diploma or on our final, right? Okay, last question for today. Okay, so we have an iron nucleus, which has 56 protons. So iron, (56 protons. And again, a proton has the same elementary charge as an electron, just positive. Okay, so the charge of 56 protons is equal to 8.96 times 10 to the negative 18 coulombs. Okay, what is the potential energy? So of a proton, so Q of proton is 1.6 times 10 to the negative 19 coulombs. And the distance here we're given in this problem is 5.6 times 10 to the negative 13 meters. So we will use Rutherford's formula here. So EP is equal to K Q1 Q2 over the distance. EP is equal to Coulomb's constant. Q1 can be our iron, so 8.96 times 10 to the negative 18 coulombs. Q2 can be our proton, 1.6 times 10 to the negative 19 coulombs. And our distance is 5.6 times 10 to the negative 13 meters. Okay, we'll punch these into our calculator, and rounded with sig digs, we get a value of 2.3 times 10 to the negative 14 joules. All right, so as we know, Rutherford's atomic structure did not last for too much longer. Pretty much in the same year, Bohr's model was revealed, where we had, well, we'll talk more about Bohr's model next lesson. But yeah, so Rutherford's model was short-lived, because if this were true for atomic structure, in accordance with Maxwell's theory of electromagnetic radiation, the electron, as it is orbiting the positively charged nucleus, it's accelerating, right? It's constantly changing its direction. Acceleration is a vector quantity. But yeah, so as it continues to orbit, it should lose energy, and that energy would be emitted in the form of EMR. And as that electron continued to lose energy, it would spiral closer and closer towards the nucleus. Okay, we know this is not the case. And as we will talk about in the next lesson, the Bohr model will have our electrons at specific energy levels. Okay. So your assignment for 15.2 and 15.3. So I want you to watch the mechanical universe for Millikan's oil drop, if you need a little bit of a refresher there. And also we have assignment 15.3, check and reflect, page 770, questions 1 to 5. So I've included the solutions to that with this post. So please take the time today to do those practice problems and compare your answers to the solutions. All right. Thank you, and we'll see you soon.